Hello, this is Dr. Zachary Roman, and I'd like to thank you for joining me for another multi-level modeling lecture. Today, we will begin with analysis of longitudinal data in multi-level modeling. And let's take a look at what we're working with. So we'll start by looking at some of the drawbacks of some traditional approaches, ANOVA and MANOVA, as well as post hoc analyses. Then we will look at the longitudinal multi-level modeling structure and an example with autism data. We'll also talk about rescaling in the example as well as polynomial trends. I will also release one more video using R, which will go through the autism example in detail so we can see the results and how I approach analyzing the data. So overall, we have some advantages of repeated measures designs. We increase power because subject-specific within variance is reduced. So in cross-sectional designs, let's say we're comparing two groups on some treatment. What we do is we use covariates or grouping factors to try and reduce inter-individual differences between the units. This, the cases or whatever we're working with. This allows us to get an idea of the effects of interest. Say if we're looking at salary, IQ predicting salary, we want to control for things like gender and education to give us an idea of the treatment effect when controlling for those things. Now, the advantage of repeated measures is that many of those things are controlled simply by the fact that we're measuring the same individual at multiple times. And so we have more control. We have, instead of statistical control, we have methodological control because within subjects designs reduce this within variance because subjects are more similar across time. Also, we can look at trend tests. So we can look at the development of some relationship across time. It's more informative. Now we have two kinds of general longitudinal data. True longitudinal data, which has the same variable measured t times, so repeated measurements of the same variable. We could also have the same variable measured under different experimental conditions. This is still considered longitudinal, however, it's a different approach. So this would be like if I took 0 milligrams of caffeine and did a reaction time test, and then took 10 milligrams of caffeine and did a reaction time test, and then 30, etc. Okay? And so that is an experimental design with repeated measurement. So how do we model these things? If we have a large number of measurement occasions, some people will say 30 or greater, or 3,000 or greater. We use something called autoregressive models or time series models. Longitudinal and time series models do greatly differ. ARMA is a common time series model for many measurement occasions, and it stands for autoregressive moving average. I won't talk much about ARMA, but the general idea with autoregressive time series models is that we're using something called lags. So to predict my time 2 weight, I would predict it with time 1. To predict my time 3 weight, I could predict it with time 2 and time 1, something like that. And the term autoregressive, auto meaning self, means that we have autocorrelation, or that my measurements in time are correlated with one another. ARMA models take that into account. We can also look at state space models, which is an approach you'll see in many different fields. But this is another means of looking at the inner workings of variables under many time points. And this allows us detailed modeling of individual trajectories. Now, if we have fewer measurement occasions, maybe 4, 10, 15, we can use traditional methods like a t-test, multivariate or univariate ANOVA, and this models our average change. Now, modern approaches like multi-level modeling and latent growth modeling, as well as many, many more within the structural equation modeling framework, if you're familiar with that, exist. And now we're modeling the average change and the inter-individual differences in change across time. And that's what we'll be focusing on in this class. So first I have to take a step back though, and let's take a look at repeated measures ANOVA. So here we have the y variable being measured for n subjects at t times. Factor A sub t, so factor A measured t times, is a within factor. Under each condition, factor B is a between factor with two levels. So we have a within and between situation here. So let's come up with an idea. So factor A would be the within factor, and that would be something such as time, right? Or measurement occasions. And factor B could be between subject occasions. Like maybe we give one group no caffeine and the other group caffeine. And we measure them at multiple time points, okay? So that's a between subjects factor. And so if we look at the design matrix here we have all the subjects down to n, and factor A, this is wide data. This is measurement occasion 1 for factor A, measurement occasion 2 for factor A, measurement occasion 3 for factor A, etc. The model equation for y for t measurement occasions and j grouping factors of B is presented here. So we have the outcome variable measured for j groups of individuals I at t time points. And it is comprised of an overall mean, a subject-specific deviance from the mean, here we go, Sj. So Sji is the individual deviation from the group means. An occasion-specific deviance from the mean of A, and a residual, of course. And of course, when we're testing these factors, we're interested in the difference of the between grouping effect across time. So we have our intercept here, AB, or our interaction term, AB. When testing the effects of factor A and B, it needs to be considered that scores Y are correlated for each person. And this is the inclusion of factor S. This takes into account that our cases are correlated within themselves. So recall that we assume these models are IID. ANOVA, MLM, we assume that they are independent and identically distributed. When we say independent, we mean that cases should not have correlations with other cases that we do not account for. Again, this would be like the example of sampling spouses on accident. Longitudinal approaches like this violate that because we are actually including the same person multiple times, and that is not independent. We need to use a term to account for that, SJI here, which allows us to have conditional independence. All right, so let's say we fit the model from the last slide. This is a typical ANOVA source table. If you're familiar with this, I'm not sure if at UTSAHA they teach ANOVA in your introductory classes, but this is a pretty common way of representing ANOVA results. And so here I have the formulations conducted to result in our F statistics here. So in an ANOVA table, we will have the main effect of factor A, a main effect of factor B, the interaction of A and B, as well as that subject-specific deviance, and then the residual here. The residuals include the interaction of S and A, so the subject-specific deviances and their temporal effect, and it cannot be separated. These are mean squared, by the way. So if you remember from the regression slides, we took a look at sums of squares. These are the mean sums of squares here, okay? And so using these calculations from those original slides is how we get to our F statistics. These are only a little bit more detailed because we have the within and between effect. So now we have the mean square of A and the mean square error, the mean square of B, the mean sum of square, or the mean square of S, the subject-specific deviations, etc. And of course, our associated degrees of freedom. Now, assumptions. We assume the normality of Y on each factor level. So this is the normality of the residuals, okay? We assume normally distributed residuals. We assume homogeneity of the variance and covariances. Again, this is homoscedasticity, that the variance of the predictions are the same across our grouping factors here. Now, sphericity is an assumption, and this is the Achilles heel of the ANOVA approach to repeated measures. Compound symmetry of the covariance matrix is assumed via sphericity. So this means the covariance between all measurement occasions are assumed to be equal. That here, if we have measurement occasion 1, 2, 3, 4, we're saying that the correlation between measurement occasion 1 and 2 needs to be the exact same as the correlation between 1 and 4, or 2 and 3. This whole diagonal is uniform. It is an assumption that ANOVA makes. This is quite unlikely. This is quite unlikely. If we think of weight as an example, people's weights will be more similar the closer the measurements are in time than the further they are in time. Many things are like this. And so putting this constraint on the covariance, the assumption here of the covariance of y in different time points is very unrealistic. I have really never seen compound symmetry or sphericity hold true with observed data. So the assumption is often violated in true longitudinal data, and less likely to be violated in experimental data if true random sampling occurs. However, even then, this can occur depending on the treatment effect. So what's the take-home message here? Repeated measures ANOVA is an option. However, it has a very strict assumption that very rarely holds true. So if sphericity is violated, the F-test is going to be very liberal. So it will be too high. The F-test will be too high, and this will lead to type 1 errors. With the uncorrected degrees of freedom, we'll have the biased result. We can actually use Geiser's epsilon to correct the degrees of freedom under sphericity violations. And the closer that epsilon is to the lower bound, the stronger the sphericity assumption is violated. More or less, we just penalize it here based on K, or the number of groups. Now, the number of measurement occasion groups. Now, if the sphericity is strongly violated, we use a repeated measures at MANOVA. Now, at the end of the day, I'll say, like, yes, we can use this correction to make the F-test more reliable. But I still wouldn't recommend using ANOVA for repeated measures information, because we get less information from the analysis results than we do with more modern approaches. However, this could be a solution in a very small circumstance. Now, if sphericity is strongly violated, some would say use a repeated measures MANOVA. So MANOVA, being a multivariate analysis of variance, gives us the null hypothesis that there is no change in time. It effectively says that the outcome variable does not change across any of the time points. So now we're using multivariate representations here. So we are using bolded matrix notation. And so U here is a pattern matrix and multiplied by our means here. And B's will be our between subject factor. So Y is a matrix of responses. B is a matrix of between subjects factors. And of course, we still have our same error term. Now, there's many test statistics people use in multivariate analysis of variance. Wilks lambda is a common one because it falls in F distribution. So what are the assumptions in repeated measures ANOVA? We still have the normality of the residuals and the homogeneity of the covariances and variances. But now we don't have any assumption of the covariance structure of Y. So the covariance matrix is unstructured unless every single relationship between the measurement time points on the dependent variable is estimated. This is not very parsimonious, and this results in too many parameter estimates in a non-parsimonious representation of the data. This is the problem with MANOVA. So, to summarize, MANOVA, unstructured, non-parsimonious. ANOVA, too structured, overly constrained. Profile analysis is another option. This is testing the single effects of the within and between factors and is called profile analysis. It includes 3 null hypotheses that are tested in sequence. This is important. The group-specific average trajectories are parallel over time. So this is our interaction effect of our within and between subjects effect. So AB1, time 1, group 1 is equal to time 1, group 2, time 2, group 2, etc. And the null is that these are parallel over time. The average trajectories don't change. Then the group-specific average trajectories have the same level. The main factor, B, so just saying the groups have the same means, and that the time points have the same means. So these are our null, that the time points have the same means, the between subject group have the same means, and the interaction. So each group at each time point has the same means as each other group at each other time point. So under profile analysis, here we have A on the x-axis. So this is the trajectory across time, and then we have Y, whatever our outcome measure is. So HOA is rejected because the interaction here, so we're talking about the interaction. B2 grows across time, B1 shrinks across time. And so we have a temporal trajectory here over A, we have change, but the change is different. So group B1 at time 3 is different than group B2 at time 3. Again at time 1, not at time 2. So there is change across time between the groups. HOA rejected. HOB is accepted. The null hypothesis is accepted. Why? Well, if we completely disregard time here, we see that these groups have the same mean. So if this is a score of 3, this is a score of 2, and this is a score of 1. If we sum those up, we have 3 plus 2 plus 1, 6. The mean of group 1 is 6. Here, 3, 2, 1, 6. Again, same means for the two groups, therefore HOB is accepted, the null is accepted. HOC is also accepted here. So if we look at the mean of time A here, we have 1, so at time point 1, we sum these together, 3 plus 1 is 4. Here, 2 and 2, 4. 3 and 1, 4. So there is the main effect of A across the groups have the same means. The main effect of B across the groups, they have the same means. However, the interaction effect is significant here because the group means across time differ. Here we have a situation where we look at the null hypothesis for the interaction, HOA, okay? So we see no interaction across time. Both of these groups have similar means across time. Their differences in the developmental trajectory is not there. HOB is rejected, however. So again, 1, 2, 3. 2 plus 2.2 plus 2 versus 1 plus 1.2 plus 1, right? So this group B has a higher average than B2, okay? So we have just a main effect difference. HOC, again, accepted. We do not have change over time. There's not significant change over time. These sum to 2, these sum to just over 2, these sum to 2, okay? So we don't have a temporal growth, which we would see with change, but we do have a group difference. Here we have an odd circumstance. Our interaction is significant. Excuse me, our interaction is non-significant. We accept the null here because we see the same developmental trajectory by the groups. Group B2 at time 3 is not significantly different than B1 at time 3. Here, again, no differences. The HOB is accepted, again, because these groups have the same means. However, HOC is rejected. We do have a temporal effect here. This sums to 4, here we sum to 2, here we sum to 6, okay? So we have an overall effect of time, but we do not have an effect of the grouping factor. This is profile analysis. Long story short, this is a good example of what we really want to understand from these models. The main effects, B and C, aren't really too interesting for us. What we really want to know is there a difference in the groups in their trajectories over time and how they develop across the time points? That is our ultimate goal with these models. Trend tests are another way to talk about change across time. So we can test polynomial trends using contrast matrices. This provides information about the average type of change. So for example, if we have 5 measurement occasions, 1, 2, 3, 4, and 5, and we want to have an idea of the change across time, we can use pairwise t-tests with corrections for multiple tests, Bonferroni, Tukey, etc. This is a bit of a primitive way. Effectively, we are doing multiple comparisons between each of the time points to determine, is time point 1 different than 2? Is 2 different than 3? Is 3 different than 4? Is 4 different than 5? Is 1 different than 5? Is 1 different than 4? Etc. So this is a bit of a rudimentary way of going about things. However, what's interesting is if you use an ANOVA or MANOVA test, we will learn that if there is an overall effect, we won't have numerical information regarding what those differences really are or what the relationships in time are, just that they are different. And so these trend tests need to be used to follow up and understand the actual trajectories of change. And this can be burdensome. The problem here is by doing a bunch of pairwise t-tests, we inflate our experiment-wise error rate. If I have a type 1 error rate of 5%, but I'm doing many tests, in the end, I have a higher error rate than intended. Therefore, we need to correct these multiple tests with a p-value adjustment, and these can just simply be too restrictive and can result in type 2 errors. So this is not desirable. All right, so now let's get into multi-level models for longitudinal data. Recall that in our cross-sectional examples, level 1 is typically some individuals. It could be students, children, something, nested in schools, countries, etc. So level 2 is some higher order clustering, and level 1 is the individual. In longitudinal models, now, we treat the individual as the higher order cluster, and the measurement occasions or the observations in time are nested within the individual. So picture yourself as a population, and so you are level 2. Measurements we could obtain from you are considered level 1. So level 1 will include time-specific variables. This will be the outcome, but it could also be, it will also be the time coding factor, as well as covariates. So this could be anything, any variable would be included at level 1 that is varying across time. The level 2 variables could be things such as gender, and they describe the individual subject themselves. They are constant over time. They do not change. These would be stable traits. So again, we can have time-specific covariates on level 1 or time-invariant covariates on level 2. And it's worth noting, our outcome and time coding variables will always be at level 1. So what's our goal? We'll talk about this data in more detail in the R exercise. But our goal in longitudinal modeling is to explain individual growth and trajectories, to understand the factors related to growth or decline. In this example here, I have age on the x-axis, so this is our time variable. And then we have social skills on the y-axis here. So we have children measured at different ages, and we have growth. Our goal is to understand the factors that contribute to different types of growth trajectories. So why do some people, some students here or children, show no social development, whereas others show more? So it's worth noting we will be using the long format of data. So participant 1 measured multiple times, and their measurements will be noted by the time variable here, okay? This is long format data. So let's take a look at what a time-only model looks like. So we have an outcome variable. This could be our social skills. And then we only have one additional variable in this model, and this is the time variable, so the measurement occasion. This is simply when the dependent variable was measured at each time. Okay, so how does this model break down? We notice now that we also have measurement occasions nested in participants. TI is now our subscript here. And the error term is broken down as well into this TI, time with an individual. Okay, so we have our fixed intercept, our random intercept, fixed slope, random slope. Substituting that into the full equation we have here. Now, this is that same equation. I want to tie these parameters back to our plot here. So I want to tie these to the data. So YIT is our outcome variable. TIT here is the measurement occasions. Gamma 0, 0 is our fixed intercept. So this is the average intercept here, the average expected value when age is 0. U01 is the variance around that intercept. So how much variation do we see in the expected value of y at age 0? Gamma 10 TIT is the average slope. So this is the average slope, the slope that goes right through the middle here of all the participants. And then our random slope here of TIT is the variance. So how much on average is this slope changing depending on which individual, depending on the individuals, right? So one more time. Fixed intercept, average intercept. Random intercept, the variation or the variance of the intercepts. Our average slope, and then our variance around that average slope, okay? So those are the terms the model is estimating here with just the time variable. So now let's take a look if we want to include a time invariant covariate, like a stable trait such as gender. So now notice that we have predictors within the level 2 equation because these are associated with I, just the individual. They do not vary T by time. So when we substitute this into the equation, what do we have? We still have our fixed intercept here. This is our average intercept. We now have Gamma 01, which is explaining variation in our intercept, right? So if this is gender and we have gender coded 0 for female and 1 for male, this equation is providing us the means to look at the average intercept when you are 0 on Z, so female, okay? So this is the fixed slope associated with the intercept here. This is what's conditioning this equation to provide us with the average intercept at with the level 2 trait. And then, of course, our variance around the intercept. Gamma 1, 0 being our fixed slope, the average slope. We now are conditioning that on our stable trait here. So the average slope when gender is equal to 0, right? Okay, so now we have deviations. Comparing male to female, we have this term which gives us a deviation in the fixed slope based on that factor, okay? And then, of course, the variance around that. So breaking that down, average intercept when you're female, using our Z example here, this is the term that gives us the difference in the average intercept for male and female. We have the variance of all of the intercepts by I. We have the fixed slope of time, so the average effective time, and then the deviation here, the average effective time, the difference in the average effective time when you're male or female, the slope difference, and then we have the variance of the slope of time, the random part, and of course our residual. Okay, so this is how the equation works out when we have time invariant covariates. Things get more complicated with a time varying covariate. This math will blow up pretty quickly here. Okay, so now xit is a time varying covariate. Again, notice the it, this varies by time. Okay, so we could think of this as something like math ability. Maybe if you're better at math, you have more social skills. So in this example, okay, so x is one vector of math ability, and it varies by individual and time, so time varying. Because it's time varying, it doesn't make much sense to just include it in the model without interacting it with time. Because this main effect will just tell us the effect of x when t is 0, we really want to look at the interaction effect to understand anything. So now we have an interaction effect in our model, right? So the main effect of time will tell us the developmental trajectories when x is 0. The main effect of x will tell us the the relationship between x and y when t is 0, so at time point 0. But the interaction effect here is what we really want. For a 1 unit increase in time, how much does the slope of x related to y change? Okay, so this is the interaction term we care about in our time model, right? So now we have just the time varying covariates in here, no time invariant covariates. The substitution is quite simple. So substituting our random effects into the equation here, what do we have? We have, again, our overall, our fixed intercept. So when time is 0 and x is 0, what is the expected value of y? This is on average across all subjects. We then have the variance term around that. Again, this is just the variance of the intercept when time is 0 and x is 0. Gamma 1, 0 is the slope of time when the fixed slope of time when x is equal to 0, okay? The average slope or developmental trajectory when x is equal to 0. And then we have a variance around that. So then we have our random term here, or the variance of the slope of time. Again, still a main effect though, not what we're too interested in. But these must be in the model for the interaction to make sense. Gamma 2, 0, the fixed slope of x at time 0. X related to y when time is 0. And then the variance of that term. How much variation in that slope exists? Now, this is the term that we're most interested in. The average interaction effect here, or the fixed slope of x times t. This term tells us for a 1 unit increase in time, so from measurement occasion 1 to 2, how much change in the relationship or the slope between x and y do we see? Okay, so this is telling us the change in development, the change in the relationship between a variable due to time. And then, of course, our random effect for this interaction, right? This tells us how much variation do the individual trajectories see regarding that interaction. And then our residual term. Okay, so let's take it up one more size. This is what the model looks like when we have a single time-varying covariate and time-invariant covariate, okay? So here we have the interaction effect that we're interested in here at level 1, the time-varying covariate multiplied by time, right? And then our time-invariant covariate, like gender, is now here. Okay, so let's break this down. Gamma 0, 0 is our fixed intercept. It is the average intercept when you are female, which is our reference category in Z, at time 0 and your X score is 0. We then have the deviation from that. So what is the difference in the male intercept compared to the female here? We then also have the variance overall. What is the variance of the term? Okay. When all variables are 0. Fixed slope of time. Average slope of time when you are female and your X value is 0. Average slope. Plus our deviation. So when you are, what is the difference in the slope, the fixed slope, compared from male to female? What is the difference of the slope of time of male to female when X is 0? Plus our deviation in time. So what is the variance of the slope of time under those conditions? We have the average slope of X. So when you are female and time is 0, what is the slope of X? We then have the deviation here. So what is the difference in the slope of X when time is 0 between male and female? And then, of course, our random term here. How much variance do the cases see in that relationship? And finally, the term we're really interested in here. Gamma 3, 0 is the fixed slope of the interaction of X and T. So this is saying, again, when Z is equal to 0, so when you are female, a 1 unit increase in time corresponds with an expected gamma 3, 0 change in the slope of X on Y. I know that's a lot to break down here. Again, the average slope for the interaction of time and X. 1 unit increase in time, the relationship between X and Y changes concurrently while you are female. What is that? Then our term here tells us the deviation from male and female. What is the difference in that interaction effect when you are male compared to female across time? Finally, of course, our variance term. So across individuals, how much variance do we see in that effect here? And of course, our residual term. Okay. So that is the general formulation for multi-level models with longitudinal data. Going back up to the top here, we can do just a time model where we're just looking at developmental trajectory over time. We may also have stable traits that we want to include. These stable traits do not vary across time, and this is how the model's formulated in that context. We may have variables that vary in time. In that case, we need to interact them at level 1 with our time variable. Or we may want to include both, at which case there's a lot of terms in the model, but if we take our time and break it down, they all make sense to us, right? So to help put this all together, I will be doing an R example with the data from the plots you saw in this lesson today. And it is data taken from West Welsh and Galecki. And it is a sample of 158 children who are autistic. We have measurement of their social skills and then their speaking competence at the age of 2, SIGDEP. This is a level 2 variable. And then for the measurement occasions, we have different years they were born. Or excuse me, different years they were measured. So they're measured at 2, 3, 5, 9, and 13. We want to model the developmental trajectories and answer the question if the development of social skills can be predicted early by speaking competency of the children at 2. So we want to look at a level 2 covariate, and we want to understand how this plays a role in social skills development. Now, it's worth noting in this example, and generally in longitudinal models, that the time factor itself can largely be arbitrary. So I have some different examples here. Recall that the intercept will give us information when x is 0, or all x's are 0. And so it's important that we consider changing the time representation variable because of how it can impact the variance. Here, the data doesn't change at all if we change the x, right? We still see the same relationships, we just slide the plot over. However, the variance term we observe at different 0 points will be very different. And so sometimes you may fit the data here and have a non-significant variance term for the random effect of the intercept. But simply moving the data by centering age or subtracting from the time variable can give us drastically different variance estimates for the intercept. I will show you a little bit about this in R, but this can be subjective in how to handle this. Sometimes it's just more parsimonious to not estimate the random intercept, center the data at a 0 point, and move forward with just a random slope. Or maybe starting values at time point 0 are really important. So your decision on scaling of the time variable will be dependent on your specific circumstance. My best advice is to look at a plot of the data and ask yourself if the expected values of our participants at the first measurement time point makes much sense. Something to consider. All right, well, thank you very much, and I will see you guys over in the R video.